And so the midterm exam is on Wednesday, March 15, 11 to 12:40, in person in Gillette, room 205. So
I have a question. Do you do review sessions or no?
yeah. So I do a review session, and also the problem sessions are always review sessions. So,
Okay, thank you.
and let's see. Remember, there's no class in CUNY on Monday, the 13th. And also on Monday, the 20th. So the next class is a week from today. So just keep that in mind. So we started to talk about the derivative. And are there any questions about the definition of the derivative, the concept of the derivative, any of the things we began to talk about on Monday? So everyone should have the book online. There's absolutely no reason to buy it. It's very expensive and completely unnecessary. And you have it for all 3 semesters of calculus at the same price if you choose to take them. If you're a math or computer science major, you have to take 3 semesters of calculus. Probably also if you're a physics major. So the concept of derivative is simple and basic. You have a curve. So say this is the graph of the function y equals f of x. And, oh, excuse me 1 second. So we have a function y equals f of x. And what we want to do is try to understand the function at some point on the curve. So this point on the curve would have coordinates x equal a and y equals f of a. And this can be a very complicated curve. And what's not a complicated curve, what's probably the least complicated curve there is a straight line. So one idea of the integral is to, let's say, we want to approximate the curve y equals f of x by a straight line through the point on the curve with coordinates a and f of a. That's the idea. So how do we find a curve that's approximately equal, a straight line that's approximately equal to the curve? That means that's close to the curve. So you can always take another point on the curve. So let's say you go from a to a plus h, and you look at the point on the curve when x is equal to a plus h, and you draw this line connecting them. So this line is called a secant line. And this is the line going through 2 points. And they teach you in pre-calculus how to find a line going through 2 points in the plane. If you had points x1, y1, and x2, y2, how do you find the equation of the straight line through those points? Well, this is one point the line goes through, and the slope of this line, slope is rise over run. So this goes from x1 to x2. So this horizontal distance is x2 minus x1, and it goes from y1 to y2. So this vertical distance is y2 minus y1, and the rise over the run, which is the vertical change divided by the horizontal change, that's the slope of this line. So we can call that m. So we're trying to find the equation of the line through a point with a given slope. We have the point slope formula. So the line through a point x1, y1 with slope m is y equals m times x minus x1 plus y1. That's the point slope formula. And if this is the slope, so we get the equation for the line through 2 points is y equals slope y2 minus y1 over x2 minus x1 times x minus x1 plus y1. So this is the equation of a line going through 2 points, right? If you haven't seen this, and this is the equation of a line going through a point with a given slope. And these two you absolutely positively have to know by heart, not, you have to know these things. This is really important pre-calculus. So if you have, let's come back to our problem. We have a curve. We want to understand the curve near the point A. We want to approximate the curve by a straight line. If I take a nearby point at A plus H, I have a secant line, and I can calculate its slope. And with this picture, the slope of the secant. So here's my curve, here's my secant. This point has coordinates a comma f of a. This point has coordinates a plus h, f of a plus h. And the slope of the secant is f of a plus h minus f of a over a plus h minus a, which is f of a plus h minus f of a. Here the a's cancel over h. And the idea is if I take points h getting closer and closer to 0, so a plus h is getting closer and closer to a, I get a sequence of secant lines and a sequence of their slopes. And if this sequence of slopes has a limit as h goes to 0, then the slope of the line, the slope that you get is what should be the slope of the tangent. So the slope of the tangent line at x equal a is the limit as h goes to 0 of f of a plus h minus f of a over h. And we call that, so that's the slope of the tangent line, and that is what is called the derivative. This is the derivative of f of x at x equal a, is this limit if it exists. And if it exists, then here's my point on the curve, a f of a, and I have my tangent line. And the tangent line has slope f prime of a. So the equation of the tangent line, it's the line through the point a comma f of a with slope f prime of a. So the equation of that line is y equals the slope f prime of a times x minus a plus f of a. So that's the slope of the tangent line. And this line approximates f of x near the point x equal a. So we have a curve. We have a problem in geometry to find the tangent to the curve at a given point. We have a problem in computation to approximate this complicated function by a straight line near a point. That's the tangent line. And this is the equation of the tangent line. And we have another definition, interpretation of this is if your variable is time and the function is telling you the position at a given time, the secant line has a slope, which is the average velocity over a certain time interval. And the tangent line has a slope, or the derivative is the instantaneous rate of change of your function at a certain point in time. So the velocity, the instantaneous velocity of a point. So all of this is discussed in the very first section of chapter 3.1. And this is the core idea in calculus 1 for the derivative. So let me do some exercises, right? So I always like to look at the exercises at the end of the section. So this is section 3.1. Suppose I look at exercise 23. So we have a function f of x equals 3x squared minus 4x, and we want to find the equation of the tangent line at the point P on the curve when x is equal to 1. And when x equals 1, f of x is 3 minus 4 is minus 1. So this curve goes to the point 1 minus 1. And what's the equation of the tangent line? So for that, we have to find the derivative. And let's see. Actually, what derivative have we calculated? Well, let me compute the derivative. Let me just compute the derivative of this function at a point x equal a. So f prime of a is the limit as h goes to 0 of f of a plus h minus f of a over h. So I have to do this calculation. This is the limit as h goes to 0, something divided by h. What is f of a plus h? If I let x equal a plus h, I get 3 times a plus h squared minus 4 times a plus h minus f of a minus 3a squared minus 4a.
Professor,
Yes,
so we basically just have to substitute.
what do you mean by substitute?
the f of a plus h into the equation?
Well, this is the function f, so f of a plus h is equal to this.
Oh, okay.
You need to do that. Let's look at this numerator. Let me just calculate this separately just to do the calculation. What is 3a plus h squared minus 4a plus h? So a plus h squared is a squared plus 2ah plus h squared minus 4a minus 4h. So this is 3a squared plus 6ah plus 3h squared minus 4a minus 4h. That's this expression in brackets. That's this. And then I'm subtracting this. So I have this, and I'm subtracting 3a squared minus 4a. And you'll see that this plus 3a squared and minus 3a squared cancel. And minus 4a and minus times minus is plus 4, they cancel. So I'm just left with these three terms. So in this numerator, let me just write it down. This is now the limit as h goes to 0. This numerator consists of 6ah plus 3h squared minus 4h over h. And I can factor out an h and cancel the h in the denominator. So this is the limit as h goes to 0 of 6a plus 3h minus 4. Right? I factor out an h and cancel the h. And as h goes to 0, 6a is still 6a, 3h is 0, and minus 4 is minus 4. So what I've done is just compute a derivative. I've shown that if f of x is 3x squared minus 4x, f prime at any point a is 6a minus 4. So in particular, when a is equal to 1, f prime of 1 is 6 times 1 minus 4. 6 minus 4 is 2. So if I want the tangent line, remember, here's the problem. Here's a function. Find the tangent line when x is 1 and f of x is minus 1. At that point, the derivative is equal to 2. So the equation of the tangent line is y equals the slope 2 times x minus 1 plus minus 1. So y is 2x minus 4. So let's see if I can actually sketch a proof of this. So if I have f of x equals 3x squared minus 4x, this is a quadratic with a positive leading coefficient. So we know this is some parabola opening up. Let's see if I can figure out what it looks like. See, this is the same as x times 3x minus 4, or x times x minus 4/3 times 3. So this is 0, 1, and 2. This parabola is 0 at 0 and 0 at 4/3. And between 0 and 4/3 is 2/3. And f of 2/3 is 3 times 2/3 squared minus 4 times 2/3. That's 3 times 4/9 minus 8/3. This is 4/3 minus 8/3. That's minus 4/3. So So at when x is 2/3, this is minus 4/3. So this is the vertex of the parabola. Parabola looks kind of like that. And when x is 1, this function is minus 1. So this is my curve passing through the point 1 minus 1. And the tangent line there we just calculated. Is that right? Let's see. Y is, no, 2x minus 3. That's better. Tangent line is y equals 2x minus 3. That's the tangent line. So we started with this function, 3x squared minus 4x, and I wanted to find the equation of the tangent line. And there it is. Now, I'm doing this by hand, and it's not that hard to do it by hand, but if you're curious and you have Maple, let me see if I can graph this problem in Maple, and you can see how beautifully Maple works for something like this. So let me see if I can open a Maple window here, share screen. Okay. So can you see a Maple window? Hope so.
Yeah, we see it.
Good. So in this problem, we had the function f. Oops. See if I can get this to work properly. F is the function x goes to 3 times x squared minus 4 times x. That's my parabola. Now, if I want to plot, oops, f of x, here's my parabola. Now, it goes up very quickly. I don't want to see it that far, so maybe I'll just plot it from maybe x equal minus 2 to 2. Here we go. Or maybe I'll go to 3. That's maybe more fun. Oops. Plot f of x. X equals minus 2 to 3. All right. And I'm interested in the tangent line at 1. This should be the point 1 minus 1. Let me just do it differently. Maybe minus 1 to 2. Okay. So you can see when x is 1, the function is minus 1. What's the derivative of f? So if I take the command in Maple for finding a derivative is just capital D of f of x. The derivative is 6x minus 4. And we're interested in the value of the derivative evaluated at 1. And that's 2. That's exactly what we saw. So the tangent line, I'll just give it a name, tangent line, why not, is y equals to the derivative of f at 1 times x minus 1 plus the value of the function at 1. And that's the tangent line, just what we got a moment ago. So now let me plot two things together. Let me plot f of x, comma, tangent line. Oops, f of x. Why doesn't this want to work? Oh, I have two curly brackets. It should only be one. Perfect. Here's the curve, and here's the tangent line. You'll notice 1 unit horizontally is from here to here. 1 unit vertically is from here to here. So this is not drawn to scale. If I want it drawn to scale, I right-click on the graph and then click on Scaling Constrained. And this is really what it looks like. Let me change this, say y goes from -4 to 4. There we go. Okay. So now this is drawn to scale. Here's my parabola, and here's my tangent line. I mean, it's really lovely what Maple can do. So you may not have, probably have not yet learned all these commands in Maple yet, if you're lucky enough to use Math 155 for Maple, but that's what it can do. Okay. Any questions about that? Let me do another example from the text. So this is again in section 3.1. Problem 43. Find the derivative of the function f of t equal 1 over t plus 1 at the point a equal to 1. So I want to calculate first f of 1 plus h minus f of, well, not first. What I have to calculate is f of 1 plus h minus f of 1 over h. So f of 1 plus h, my function is 1 over t plus 1. So when t is equal to 1 plus h, this is 1 over 1 plus h plus 1, which is 1 over 2 plus h. And f of 1 is 1 over 1 plus 1, which is a half. And f of 1 plus h minus f of 1 then is 1 over 2 plus h minus 1/2. Now, I assume by the time you make it to calculus, you know fractions. So if I put this over a common denominator of 2 times 2 plus h, this is 2 minus 2 plus h. The 2's cancel. I get minus h over 2 times 2 plus h. So that's what this numerator is. And I need to take the limit of this quotient as h goes to 0. So that's the limit as h goes to 0 of minus h over 2 times 2 plus h over h, which is the same as the limit as h goes to 0 of minus h over 2 times 2 plus h times h. And the h's cancel. So this is the limit as h goes to 0 of minus 1 over 2 times 2 plus h And as h goes to 0, 2 plus h goes to 2, and 2 times 2 is 4. So this is minus 1 over 2 times 2, or minus a fourth. So for my function f of t equal 1 over t plus h, f prime at 1 is equal to minus a fourth. All right. Now, I would suggest you take a piece of paper and a pen or a pencil and go through this calculation. Maybe not now after class, but this is exactly the type of problem that will be on the midterm. This is calculating a derivative directly from the definition. Okay. Any questions so far? So what we've seen is that given a function, f of x, we can calculate the derivative at any point x equal a. Call that f prime of a. But if you can do it for any point, we can just as well call the variable x. So we have the derivative of the function is f prime of x. So for example, in the problem I considered a moment ago, where f of x is 3x squared minus 4x, then we saw that for any point a, f prime of a is 6a minus 4, or if you use a, x is the name of your variable, f prime of x is 6x minus 4. So here we have a function, f, and we get a new function from it, the derivative. And there are lots of alternative definition notations for, so other notation for derivative. And you see these all the time in mathematics. So you have df dx, or the derivative with respect to x of f of x, or capital D sub x of f of x, or sometimes just f prime of x, or y prime of x, or d of f, right? So all of these mean exactly the same thing. They're just different notations for a derivative. And I should also say dy dx. So if you have the function y equals f of x, you can write the derivative as dy dx, df dx, f prime of x, y prime of x. They all mean exactly the same thing. I should also make one other observation. So if you have a function, y equals f of x, the derivative, dy dx, or f prime of x, is the slope of the tangent to the curve y equals f of x at the point x. So if dy dx is positive, the tangent has a slope, dy dx, which is positive, that means on the curve, the tangent line has positive slope. It's going up. If dy dx is negative, the tangent has slope dy dx negative. That means at that point, the tangent line is going down. And if y dx is 0, the tangent line has slope 0. A line with slope 0 is a horizontal line. So at this point on the curve, where you have kind of a maximum, the slope of the tangent is perfectly horizontal, parallel to the x-axis. And so from the sign, positive or negative or 0 of the derivative, you can tell whether the curve, the tangent line is going up or down or horizontal. And you can tell whether the function roughly is increasing, decreasing, or has like a peak or maybe even a minimum or something else. I mean, 0 tangent. As tangent equals 0 is a little bit more complicated. Now, it's very important to observe that derivatives don't always exist everywhere. So suppose we take the function f of x equals square root of x. So we know what that looks like. When x is positive, absolute value of x is x, or when x is equal to 0. But if x is negative, the absolute value of x is minus x. So for x positive, this function looks like the line y equals x. And for x negative, it looks like the line y equals minus x. So that's the graph of the derivative. Sorry, that's the graph of the function, absolute value of x. Let's calculate the derivative. So if x is positive, so here you take a point x, which is positive, f of x plus h minus f of x, if h is small, so if x is positive, and so here's x, and let's say this is x plus h, and this is x minus h, still positive, x minus h greater than 0. In this whole interval, this is all positive. It's all to the right of 0. So f of x plus h minus f of x over h is equal to, remember, f of x equals x when x is positive. So this is x plus h minus x over h. The x's cancel, you get h over h is 1. So the derivative f prime of x equals 1 for x positive. So for the absolute value function, if x is positive, the derivative is 1, which of course you can tell because this straight line, tangent line is equal to itself, has slope 1. Suppose we have x negative, and we take some small value of h, so x plus h is still less than 0. In this case, so for x less than 0, f of x plus h minus f of x over h, if x and x plus h are negative, f of x is minus x. So this is minus x plus h minus x over h. This is minus x minus h plus x over h. The x's cancel, you get minus h over h and minus 1. So f prime of x is minus 1 for x less than 0. So for x less than 0, slope is minus 1. So for this function, the derivative is 1 when x is positive and minus 1 when x is negative. What about at x equals 0? So if h is positive, f of x plus h minus f of x over h is 0 plus h minus 0 over h is h over h is 1. So this quantity is 1 if h is positive. But if h is negative, f of x plus h minus f of x over h, x is 0. This is really f of h minus f of 0 over h. This is minus h minus 0 over h. Minus h over h is minus 1. So around x equals 0, if you're a little bit to the right of 0, this quotient is 1. If you're a little bit to the left of 0, this quotient is minus 1. So if you take the limit as h goes to 0, it doesn't exist. Because from the right, the limit is 1. From the left, the limit is minus 1. So f prime of 0 does not exist. And in fact, if you wanted to graph the derivative, it's 1 for x greater than 0. It's minus 1 for x less than 0. And at x equals 0, it doesn't exist. So that's really very important to know that derivatives do not always exist. Okay. Any questions about this? This is all just trying to get a feeling for what the derivative means. Now, suppose you're given a curve. Like suppose you have the curve y equals 2 to the x. This is an exponential curve. Graph looks like this. What can we say about this? First of all, so this is my function f of x. Right? So let's say we want to describe the derivative of this function. So let's make some observations. First, at any point, f prime of x is positive. This function is always increasing, and wherever you draw a tangent line, it's going to have positive slope. Second, if you look at these tangent lines, the slopes get bigger and bigger and bigger. So not only is f prime of x positive, but it's increasing. This exponential curve is increasing faster and faster and faster. And in fact, f prime of x goes to infinity. Not only is it increasing, but it increases beyond any limit. So what's an example of a situation where you might see some process that's described by this exponential curve? Well, in biology, you might get a petri dish and put in a bacteria. And then, let's say, the bacteria grows and divides, and you get 2 bacteria. Let's say it takes, 10 minutes for a bacterium to grow and divide. So 10 minutes later, you have 2. And 10 minutes later, each of these divide, and you have 4. And 10 minutes later, these each divide, and you have 8. And this function is increasing, we say, exponentially. The number of bacteria at time n will be 2 to the n. So you think, oh my God, I have this bacteria and it starts to duplicate, to replicate, and exponentially. And pretty soon the Petri dish will be too small to hold them, and they'll spill over the sides and still keep growing and take over the lab and take over the building and keep growing, take over the campus, keep growing, take over the Bronx, New York City, New York State, take over the whole world. Well, you know that doesn't happen in real life, because at some point they can't just keep growing and dividing. They run out of food and they're competing for food. So what you would typically see in making experimental observations, and then the mathematical model of the growth of bacteria, is you'll start with some initial population, maybe one, and in the beginning it'll grow exponentially. But then there starts to be a lack of food and a lack of space, and they'll still be increasing, but it'll be more and more slowly. And in fact, there'll be some horizontal line that this population is approaching, as we say, asymptotically. So the population is growing according to some function, let's say P of t, the population at time t. This is the population at time 0. It goes up fast, and then it starts to slow down and hits some limiting population. This is sometimes called the logistic curve. And many processes in nature have a mathematical model that fits this, that looks like this curve. So this is always increasing. The slope is always positive. So for this curve, P prime of t is greater than 0 for all t. I'm only looking at positive time. And P prime of t itself is increasing. So the population grows exponentially in the beginning, faster and faster and faster. But then it hits some point where it's still increasing, but then it's decreasing. So this curve has positive derivative everywhere. It's approaching some horizontal line asymptotically. That would be the maximum population that the environment can sustain. And if you look at the rate of change of the population, it grows exponentially in the beginning more and more quickly. And then the rate of increase is still positive, but it's decreasing. And eventually, it's not constant exactly, but it's almost constant. It's approaching asymptotically some limiting population. And this is a very, very important type of curve in applications. Any questions about this? All right. Well, how do we calculate derivatives? A large part of this class in the beginning, in the first half of the semester, is learning how to calculate derivatives. So one method is you calculate derivatives from the definition. F prime at x is the limit as h goes to 0 of f of x plus h minus f of x over h. And this is a necessary skill to learn, but in general, this is hard and messy. So it would be useful to have some rules to speed up the process. And there are a number of rules of differentiation. I will prove some of them next class, which is next Wednesday, but I just want you to see them today. So the first rule is called the constant rule. Suppose you have a function f of x equals c. That's just a constant. So the graph, this is the graph, f of x equals c. It's a horizontal line. A horizontal line has slope 0. The tangent line to a line is the line. So f prime of x is 0. Right? The tangent line is horizontal, has slope 0. So that's the constant rule. Right? That's kind of obvious. Extremely important is the power rule. It says if you have x to the power n, so I'm using this notation d dx, the derivative of x to the n is n x to the n minus 1. So the derivative of x squared is 2x. The derivative of x cubed is 3x squared. Okay, that's the power rule. There is a constant multiple rule. It says if you have a function f of x and you multiply it by a constant c, the derivative of c times f of x is c times the derivative of f of x. So you can take the constant outside, or c times f prime of x if you like. There is the sum rule. If you have two functions, f of x and g of x, and you add them, and you take the derivative of the sum is the sum of the derivatives. We also have the product rule. If we have two functions, f of x and g of x, and we multiply them, now this one's getting a little bit trickier. The derivative of the product of two functions is the derivative of the first function times the second, plus the first function times the derivative of the second. So that's more complicated to remember. And even more complicated is the quotient rule. If we have functions f of x and g of x, and we divide them at a point where g of x is not 0, so you can't divide by 0, the derivative of the quotient of two functions has the following complicated form. It's going to be a fraction, a quotient, and the denominator of what you're differentiating, that squared is your new denominator. And in the numerator, it's f prime of x times g of x minus, not plus. Here we had plus, here it's minus f of x, g prime of x. So these are our rules. And so, for example, if f of x is 7, the derivative of the constant function 7 is 0. Of f of x is x to the 5th. By the power rule, f prime of x is 5 x to 1 less than the exponent, 5 minus 1, 5x to the 4th. So f of 7x to the 5th, you can take a constant outside, that's f prime of 7x to the 5th, is 7 times f prime of x to the 5th, which is 7 times 5x to the 4th, which is 35x to the 4th. If we have 7x to the 5th minus 11x cubed, and we want to differentiate this, let me write this plus, just make it easier. By the sum rule, this is the derivative of 7x to the 5th plus the derivative of 11x cubed. By the constant rule, this is 7 times the derivative of x to the 5th plus 11 times the derivative of x cubed. That's 7 times 5x to the 4th plus 11, derivative of x cubed by the power rule is 3x squared. So this is equal to 35x to the 4th plus 33x squared. Let's actually do an interesting check. If I take 7x to the 5th times 11x cubed, let me differentiate this by the product rule. So this would be the derivative of 7x to the 5th times 11x cubed plus 7x to the 5th times the derivative of 11x cubed. The derivative of 7x to the 5th we saw is 35x to the 4th times 11x cubed plus 7x to the 5th, and the derivative of 11x cubed is 33x squared. So what we have is 35 times 11. That's 385 x to the 4th times x cubed is x to the 7th. 7 times 33, 231 times x to the 7th. This is equal to, if you add them, x to the 7th times what? 6, 8, and 3 is 11, 616 x to the 7th. That's what it is. Okay. If my arithmetic is correct, no reason to believe it is, but hope it is. Let's do this problem another way. The derivative of 7x to the 5th times 11x cubed, I could just multiply these. If I multiply them, I get 77 x to the 8th. By the power rule, this is 77 times 8 times x to the 7th. What's 77 times 8? 8 sevens are 56. Wow. 616 x to the 7th. So we're lucky. We get the same answer doing the problem 2 different ways, which is really important. And there's a certain consistency to mathematics, which is reassuring. All right. Any questions about any of these? These are lots of rules to remember, memorize, whatever, you have to know them. On the midterm, you'll be given several functions to differentiate, and you differentiate them according to the rules, but you have to know the rules. All right, let's try one more problem. Suppose we have a quotient. Suppose f of x is x squared plus 2 over x plus 3. What is f prime of x? By the quotient rule, we take the denominator and square it. That's the new denominator. The numerator is we take the derivative of the numerator. The derivative of x squared plus 2 is 2x plus 0 is 2x times the denominator minus the numerator times the derivative of the denominator. The derivative of x plus 3 is 1. So what we get is, this is over x plus 3 squared, 2x cubed plus 6x minus x squared minus 2. So if I put this in the usual way of writing a polynomial with decreasing powers, 2x cubed minus x squared plus 6x minus 2 over x plus 3 squared. So here I have a rational function, a quotient of polynomials, and when I differentiate it, I get a new rational function. Let's do another one. I mean, the quotient rule is the hardest rule to get to use properly. Suppose f of x is 7x plus 4 over 2x minus 3. So f prime of x, you take the denominator and you square it. The derivative of the numerator is 7 times the denominator minus the numerator times the derivative of the denominator, which is 2. So this is 14x minus 21 minus 14x minus 8 over 2x minus 3 squared. The 14x's cancel, and I get minus 29 over 2x minus 3 squared. Okay. All right, now, what you really need to do is spend a lot of time, as much time as possible, computing these derivatives. There are lots of examples on MyLab in the homework problems of computing derivatives. You need to know how to do it. And you need to know how to do it by hand, because when you take the midterm, there's no computer. It's you and your paper and your brain. That's the only way to do it. Any questions about any of this? I have problem sessions, several more this week, one today, one Friday, others are, we can arrange privately if you have another time you need to meet. But it is, I don't want to go anywhere beyond what I've just done. This is a lot to master. You have the concept of the derivative, the concept of a secant line and a tangent line, the equation of a line if you know the slope and a point, how the tangent line gives you a nice local approximation to a function near the point. It uses the derivative because the derivative is the slope of the tangent line. And then we have various rules for calculating derivatives. Sum, difference product quotient. Yeah. So I think I'm going to stop right now. But again, there's a week until our next lecture. And I would hope and encourage you to spend at least some time every day practicing derivatives. It's better to do a little bit every day than to spend 10 hours one day. Not bad to spend 10 hours every day. But few people have the time to do that. But a little bit of practice every day is really the best way to learn how to do derivatives. And that's one of the minimal prerequisites for passing the course. All right, everyone. We're going to quit. Any questions before we quit? Okay, all. Be well. See you in lecture 1 week from today.